During the chapter B of the TCPIP protocol family, we will talk about the addressing functions of implemented in the IP version 4 protocol. We need to remember that every IP interface of a host or a router must have an IP address assigned. Then here in this diagram, we could see different hosts that are connected across a local area network, and those hosts, for instance, are connected across a router to other routers using, for instance, different technologies of wide area networks. And in that way, we interconnect all the networks or subnetworks using the protocol called Internet Protocol. And one of the functionalities that Internet Protocol implement is the addressing. When we talk about in the introduction to Internet Protocol, we talked about the destination address-based routing implemented in the Internet Protocol, in the Internet architecture. And the destination address-based routing could work with 3 different types of addresses. The typical first address type is the unicast. The unicast is a direction, an address, that an IP address that permits to forward datagram to only one host or router in the network. In the case of multicast, the multicast is a type of addressing or IP addressing that permits to deliver one datagram to several hosts or routers in a network, not only in a local area network, but in the global network. And finally, we could have the broadcast address that is typically used to deliver a datagram to all other interfaces in a broadcast domain, in a network, in an IP network, but within a broadcast domain. Those are the typical 3 addressing types that are supported by the IP protocol. Remember the addressing, the internet addressing implemented in IP version 4 is based in the use of assignation of a unique 32-bit internet address to each interface of hosts and routers. The upper bits of the address identify the network, and the lower bits of the address identify the host. In order to distribute the authority to assign the IP addresses to each interface, the Internet has a central organization called ICANN, Internet Corporation for Assigned Names and Numbers, and IANA, Internet Assigned Numbers Authority, that are responsible for this. Those organizations distribute authority to other country or regional organizations. For instance, the RIR or the RIPE, NCC, and other countries, for instance, each country could have an authority to distribute the net blocks, the IP addresses that the different organizations could assign to their networks and interfaces in each network. In order to then to distribute the network addresses, the 32 bits of the IP version 4 address are divided into different classes. Remember that the classification is the division of a certain set of things, for instance, in this case, addresses, into different groups. Those groups are I mean, those groups or set of addresses are disjoint. Then we classify the addresses into different classes. The first class, the class A, is intended for very large organizations. The classification includes one class identification bit, only one. The most significant bit in this case is 0, and the 7 network bits and 24 computer bits. We could see this in this picture. The class A then has in the class A, the addresses has the most significant bit 0, 7 bits to code the network, the network number, and 24 bits to code the host, to identify the host. In the case of the class B networks, that is the two most significant bits are in 1 and 0, and in that case we use 14 bits, and those 14 bits to identify the network, and 16 bits to identify the host. That is class B addresses are intended for large to medium-sized organizations. And the last important class is the class C, is intended for smaller networks, for example, a corporate network. And the classification consists of 3 class identification bits, 2 in 1 and 1 in 0, 21 network bits, and 8 computer bits. That is, for instance, in this case, the class C use those bits to identify the class, the most significant bits in 1, 1, and 0, 21 bits to identify the network, and finally 8 bits to identify the host. The class D and class E addresses. The class D addresses are used to multicast addressing, and the class E is reserved for future use, and typically in the case of IP version 4, no assignation is performed until now. Then remember, the structure is we identify with the most significant bits, we identify the class of the address. In the case of class A addresses, the first octet is used to identify the network. In the case of class B, the two most significant octets are used to identify the network, and in the case of class C, the three most significant octets are used to identify the network. And we typically use different notations, but the most used notation used in IP version 4 is the dotted decimal notation. The dotted decimal notation, we code each octet in decimal, and the notation use a dot in order to separate the decimal numbers of each octet. With this method of notation, we could read easier the addresses. I would like to show you another way of present the different classes. Then for each of those classes of addresses, A, B, C, D, what is important is to identify the class with the most significant byte or most significant octet. Then, for instance, all the addresses, the IP version 4 addresses that has the most significant octet between 0 and 127 are class A. The net number is represented by the most significant byte, and we will see that in that case we use Netmasks default of 8 bits, but we will talk about the Netmask later. In the case of the class B addresses, the most significant octet of the address is in the range of 128 to 191. Remember, in the B class, we have the most significant bit in 1, and the next most significant bit in 0. Then that's why the addresses between those numbers are class B addresses. In the case of class C, this octet, the range of this octet is between 192 and 223. And in the case then of class C, for instance, the three most significant octets represent the net number. Then we return to the lecture, the point of the lecture, and then remember that kind of rule to identify quickly which is the class of any address. For instance, in the case of this address, the most significant octet is 193. That means that in fact is a class C address. And if we represent this number in binary notation, we could see that in fact the most significant bits of this octet are in 1, 1, and 0. Then is a class C address. And then now we need to understand another concept is the use of the netmask. The division of the addressing space in only 3 classes, class A, B, and C, is not enough to administer correctly the address space, and we need to implement another mechanism in order to improve the use, the optimal use of the addressing space. And there are another two problems typically. The central administrative effort for address management that increased sharply, and the route tables that increased significantly. Then we need to introduce an additional mechanism in order to typically reduce the effort for central administrative addressing assignment, and to reduce the size of the routing tables. To solve these problems, the addressing scheme has been extended by the subnet concept, and then only one network address is assigned per organization, but the class of this address depends on the number of networks and computers of the organization needs. Within an organization, the computer field of the address, which can also be called local field, is now further divided into a network field, the subnetwork field, and a computer field. That is, the IANA, for instance, assign a network number like this to an organization, and the host part of those addresses could be used by the organization, for instance, corporation, a university, an internet service provider. Then those organizations could use this range of addresses, but they could use the most significant bit of the host part to identify the subnetwork, and the less significant part of the host part to identify typically the host within the subnetwork. And then if subnets are used within an organization, a so-called subnet mask must be selected. This mask divides the local address field into the subnet and the computer part. Then the new terminology, the new concept is the net mask. The net mask consists of 32-bit number, and the network and subnet fields are represented in the mask by set bits, and the computer or host part has null bits. That is, this number, this 32-bit number, in fact, is a number that has n bits, the most significant n bits in 1, and the least significant bits, the least 32 minus n less significant bits in 0. Then the bits in 1 permit to identify the network, and the bits in 0 permit to identify the host within that network. If one computer, for instance, wants to communicate with another, it must first find out whether it is on the same network. To do this, it takes the destination address and hides the computer portion with the help of the subnet mask. This is accomplished using, for instance, typically logical operation, and then we perform the AND operation between the destination address and the netmask of the local network. And in that way, we will try to find which is the network. We will try to find out whether it is on the same network. If the destination is on the same network, we will see this particular algorithm when we talk about the routing functionality of IP protocol. But what is important to understand is that a number of 32 bits called netmask is assigned to each interface. Then each interface has not only an IP address of 32 bits, but another 32 bits number called the netmask. Then I repeat, this concept is very important in order to identify the network to which is connected, or every IP interface of a host or a router must have a netmask assigned. The netmask is a 32-bit number that has n most significant bits in 1 and 32 minus n less significant bits in 0. We could use the decimal or the dot decimal notation in order to identify a netmask. For instance, this netmask, the typical default netmask used in class A addresses. This means that the 8 bits of the most significant byte are in 1, then 255.0.0.0 is a mask that has 8 bits, the 8-bit most significant in 1 and the less significant bits in 0. But we could use another notation called /n, where n is the number of bits in 1 in the netmask. Then /8 is in fact in decimal dot notation this mask. That is a mask that has the 8 most significant bits in 1. Or for instance, this is the netmask that has 16 most significant bits in 1. That is, this is the notation used in decimal dot notation. That is 255.255.0.0 is a /16 or a /24 and so on. And then every IP interface of a host or a router must have an IP address and a netmask assigned. This is a very important concept that you need to remember. The network address permits the identification of all the interfaces that are connected to the same network. The network address has typically, for instance, is the address to identify that identifies the network. Every host bits are in 0. This is the network address of any network or subnetwork IP network or subnetwork. The broadcast address allows datagrams to be broadcast to all hosts on the same network. That is, broadcast address is an address used to deliver datagram to all hosts on the same network or subnetwork. In that case, every host bits are in 1. That is, the The lower position of the net block used by any network or subnetwork identifies the network, and the upper address in the net block in the range of addresses used by a network is reserved to the broadcast address of that network or subnetwork. How we could calculate easily those addresses, having, for instance, the IP address and the net mask of any interface? Well, the network address of the network to which the interface is connected is obtained by making the AND between the IP address of the interface and the net mask of the interface. It is a typical AND operation between two 32 bits numbers, the IP address and the net mask. The result of this AND operation is what we call the network address that identifies that network, the network to which the interface is connected. In order to calculate easily the broadcast address of the network to which any interface is connected, we need to perform an OR operation, a logical OR operation between the IP address of the interface and the net mask negated. That is, this is an operation that obtain the result of this logical operation is the broadcast address. Remember that when we perform this, if we negate the net mask, that means that the lower bits of the mask are in 1, then the OR operation will force 1 in the result. That is, this operation force ones in the host bits of the IP address, and in that way we obtain, using the IP address and the net mask negated, the broadcast address. There are some special addresses, particularly the loopback address. The loopback address is a class A address reserved to be assigned to a logical or software IP interface, typically called local interface. And I was talking about the loopback address that is assigned typically to a local interface. A local interface typically is a logical or software interface in any platform, a host or router, and that kind of interface is used only to exchange datagrams between processes of the local host or local router. The datagrams designated to the loopback address are prohibited to be transmitted over a physical IP interface to other hosts or routers. So this address couldn't be used in any internet protocol diagram, IP datagram, excuse me, IP datagram across the physical network. The n bits net mask allows the address space to be partitioned into a network or subnet of 2 to 32 minus n addresses. The lowest address is used for the network address and the highest for the broadcast address. That is, the lowest address is which has the host bits in 0, and the broadcast address is the address where host bits are all in one. And then remember, the network address is obtained performing an operation, and a logical AND operation between the IP address and the net mask of any interface of the network, and the broadcast address could be obtained performing a logical OR operation between the IP address of any interface in the network and the net mask negative. And that means that in fact the range of 2 to 32 minus n addresses already use we use two addresses, one for network address and the other for broadcast address. That's why we could use within this range 2 to 32 minus n minus 2. Then, for instance, for /24 net mask, that is 24 bits, most significant bits in one, that is this kind of decimal notation. We could have a range of 2 to 32 minus n minus 24, that is 2 to 8, and 2 to 8 is 256, minus 2 is 254 hosts. Why we could assign only 2 to 254 hosts, and not 256? Because the lower address of this range and the higher address of this range are used to the network to be used as the network address and the broadcast address. And in that way, we could calculate for different net masks how many hosts we could address using each of those net masks. Here we are another table where we could see the net mask and the net mask, for instance, a net mask of /8, and the dot decimal notation of that net mask. And here you are all the complete table that relate the net mask with the dot decimal notation of the net mask and the number of hosts, the host addresses, but to this number include the network address and the broadcast address. Pay attention that the /31 could never be used, because in this way we only have two addresses in this range with the net mask of /31. One is the network address and the other is the broadcast address, and then we can't assign any host in /31 network. But for instance, in the case of /32, that is only one address, this could be used typically for a logical or software interfaces like loopback, and that means that only one interface is a member of this subnetwork of /32 bits in one. Well, then now we need to talk about another concept, that is the net mask default associated with each class of address. When we assign the net mask to each IP address, if we don't if we don't implement any kind of subnetting, in fact, we need to assign the netmask default to the class associated with the class of the address of the interface. If the interface has an IP address of class A, the netmask default is /8 netmask. If the IP address assigned to an interface is class B address, we could assign a netmask default of 16, that is /16. And in the case of any address of class C, the netmask default is /24. This is important to understand the concept of subnetting. Then we could perform an IP addressing without subnetting, but when in every interface the netmask default corresponding to the IP address class is used. That is, and every interface in a network need to use the netmask default corresponding to the IP address class of the interface. And if we implement an addressing without subnetting, we are not able to make optimal use of our address space. That is, only the class A addresses has this mask, and the class B addresses has this one /16, and the class C has the 24, the /24 netmask. That means that class C networks could in class C networks we could assign 254 hosts, and in class B 64K addresses, and one in A 2 to 24 minus 2 hosts. But this is a non-optimal use of the address space. Then typically in internet and in any corporate network, we implement IP addressing with subnetting. Addressing with subnetting allows better use of address space because the IP address is partitioned into the network number, the subnetwork number, and the host. In each interface, a netmask with a length longer than the default netmask corresponding to the class is used. That's why we talk about subnetting and not supernetting. We implement subnetting when the netmask you assign to each interface is longer than the default netmask. For instance, if the interface is a class A, and the default mask is /8, but we could use, for instance, a netmask of /16 or /24 or /30. Remember that to calculate the network address, we need to perform logical AND operation between the IP address and the netmask. And then when you assign, when you calculate, divide the address space into different net blocks or networks or subnetworks. Always, when you perform the AND of the network address with the netmask, the result must be the network address. If the result of an AND operation between the network address and the network mask is equal to a different address and not the network address. That means that you made a mistake the addressing plan. Remember, this is very important. Then there are two types or two kinds of subnetting. The fixed length subnet mask and the variable length subnet mask, the FLSM and the VLSM. Typically, nowadays we use typically the VLSM. Why? Because we obtain the most optimal use of the address space with the VLSM, with the variable length subnet mask. But what is important to understand is which is the difference between the fixed length subnet mask and the variable length subnet mask. The difference is not that in this case we don't perform any kind of subnetting. No, in this case we perform subnetting, but when using a single net mask for the same net number partitioning, in that way, the address space of a network identified by the net number into subnets of the same size. That is, if you have a particular IP address in an interface based in the class of that address, you could identify the network number. For instance, class A, the network number is the most significant byte or most significant octet. If the address is class B, the net number is the two most significant octets, and if the address is class C, the net number is in fact the three most significant octets of the address. Then for the same net number in the network, in every interface of the network, we need to use the same net mask, the same fixed length net mask. Then all the subnets associated with the net number have the same size. This is then fixed length subnet mask. In the case of variable length subnet mask, we talk about subnetting with this scheme, variable length subnet mask, when using different net masks, that is, different length of net mask for the same net number. Partitioning the address space of a network identified with a net number into subnets of different size. And then for instance, nowadays we typically use anywhere VLSM, and with VLSM we could use to the same net number different net mask, different net mask lengths. Well, the opposite of subnetting is the supernetting or super networking, and in that case we use net mask that is shorter than the net mask default to the class. And the supernetting is used basically to identify the routes in the routing table. and then we could perform what we call route summarization or route aggregation. This is very important to reduce the size of the routing tables in the routers, particularly in the routers in the internet backbone. The internet backbone are those routers that are haven't default route in the routing table. Is what we call the default free zone. That is the zone of the internet where the routers have routing tables without default route. Then in that case, it's very important to reduce the size of the routing table using summarization or aggregation, route aggregation. Well, finally, we could talk about the relationship between the subnetting and the routing algorithm. We will talk about routing algorithm in future lecture in future lectures, but it's important to take into account that some routing algorithms support subnetting, for instance, fixed length subnet mask, or variable length subnet mask, but all the older routing algorithms only support fixed length subnet mask. Then remember, IP routing, it is the process of transferring a datagram from one host to another through intermediary nodes, that is, routers or gateways. It's based on the destination address, that is, the destination address based routing, and use the routing table to choose the route, the best route to reach the destination. And the choose of the route means that the router know which is the interface and which is the next hop to forward the datagram. Then there are typically two main routing algorithms of IP. The first algorithm that was proposed was the what we now call classful routing, based in the use of the class of the addresses and the use of the netmask, but in fact the classful routing only could associate the netmask with a net number. Then only one netmask could be used associated with each net number. Then only so the fixed length subnet mask is supported with that kind of classful routing. Nowadays, we don't use that kind of routing in any host or router. In any host or router nowadays, we use this new routing algorithm called classless routing or classless interdomain routing, that is CIDR. In order to understand the difference, in the old routing algorithm, the routing tables hadn't the route mask. But in the newer routing algorithm, in the classless routing, the routing tables have the route mask. Then we will see that in detail when we talk about IP routing. And because of that, the classless routing supports fixed length mask, variable length mask, and route summarization aggregation.